Hello everyone, welcome back. In this video I'm gonna solve the first example of designing using different approach. Now whichever you prefer, you're free to choose between them. Now in the first approach, in the first step, I aimed finding A, then I checked, then if it's correct we continue finding AS. In this approach, I shall directly find AS, then I will check the AS, then we will do a checking. Now, both approaches possible, whichever you prefer, they have their advantage, disadvantage, but whichever you follow, it's correct. Now, similar manner, we will start by first changing the service moment. So we have a service dead load moment and a service dead load live. We're changing it for MU. We said in the case of live load and dead load we have two combination, 1.4 moment dead load or 1.2 moment dead load plus 1.6 moment live load. Now this should give us the same. So if I have the moment, if I say 1.4 of the dead alone, that's going to give me 189 and 84 kilonewton per meter. In case if I want to use 1.2 times dead load plus 1.6 times live load, that's going to give us 325, which we already know this one, 325.44 kilonewton per meter. So we choose the biggest one for the design. This is still the same procedure. Now where do we start? We start with the assumptions. Still we're going to assume the same manner. So the first step we have it, assume still phi equal to 0.9, fs equal to fy, and we assume one layer of steel which is gonna give us d equal to h minus 65, which we have h here in this example, h to be 635, so 635 minus 65 is going to give us 570. Now, where do we start? We say that mu is equal to phi mn. Now in this, I can write in this manner, phi nt z. Now nt is equal to what? Still continue in this way, as fy, since we assume fs is equal to fy, this will be, and z we shall assume d minus a over 2. Now by the way, this assumption where we start here, now in a few chapters later you will realize that z has different approaches, but here we assume that we have only tension still. So indeed there is another assumption here, but I cannot write it right now because you don't know what is the meaning of that one. So even in the first approach we did it, I directly wrote z equal to d minus a over 2. Later when we follow up next chapters, you realize that z may have different approaches, different values, but we always start with this, z equal to d minus a over 2. Now in this approach, I shall look in a way that to change a to as. So I want to find as here, not a, in this approach. So this is mu equal to this. How can I change a to as? Basically we'll go for, we know that nt is equal to nc, so as fy is equal to 0.85 f prime c since we have rectangular cross section here, remember we have rectangle cross section we're designing here. Don't mind the drawing here, so let's make it like this. We have a rectangular cross section, so we want to find AS at the bottom, which we know that at the top this will be the compression block, which we call it A and B. We have B to be 250 millimeter. So since we have a T, I can write it AB, and we know that A is equal to AS Fy over 0.85 F prime C B. Then I shall substitute this one, so let's say this is 1 and this is 2. Substitute 2 into 1, I changed A to AS. Well, it needs some arrangement. I will keep going with the symbols here. Maybe later you can directly use the equation, because always will end up the same thing. AS Fy D minus, this is for A will be AS, so will be 2 on this 2 at the bottom. I have it, so AS divided by this one, it's going to be 1 over this 2 will come 1 over 2, write it like this, AS Fy, and this will be 2 times 0.85 F prime CB. We'll continue further in order to simplify this one in a way that to be solvable. We bring it to quadratic equation. So if I open up, still I will leave this mu here. This will be phi AS FYD, phi AS FYD, then minus, this will be AS square Fy square, so keep, this will be phi, I have it here, Fy will be Fy square over 2 times 0.85, I can change this one if I want to, B AS square. So in order to make this one easier for myself, I can change in a way to write AS here. Then finally, if I rearrange this one, rearrange it in a quadratic equation manner, this term will come in the beginning. So we have phi Fy square over 2 times 0.85 F prime CB. This is AS square, and this is minus, we have it in the beginning. Then plus phi Fy D AS, then minus mu. Now here, for the units, we shall be careful, equal to 0. Now this is in the term of what? AX square plus BX plus C equal to 0, which we know as quadratic equation. Now, you can use this equation. I can even write it down, put it somewhere inside the lecture notes. I mean, this is always, you end up with the same thing. Someone can do it for the first version A. You can do it like bring it to this manner. In that case, will be A square A, and there will be mu here. Now, we shall look into the values to see what will happen. So if I put minus, I'll put the values here for the units. Phi we assume to be 0.9. Fy we have it here 420 square over 2 times 0.85. F prime C, if I'm not wrong, 21, and B 250. This will be AS square plus 0.9 times 420 times 570 for D. That's going to be AS. Now here what I did, I used megapascal, which is, and with millimeter. So 250 is millimeter here, I used it. 420 is megapascal, 570 is millimeter. So we shall change this one to Newton millimeter. In the beginning, the value of mu is kilonewton dot meter. If I multiply this one by 10 to the power 6, I will change it to Newton dot millimeter. So in that case, this is the unit change. I will do it for the mu, which is 325. I'll say minus 325.44 10 to the power 6 equal to 0. It's 325.44. So I have the quadratic equation here. We'll rearrange this one a value, this will be a value, this will be a value. So if I use the quadratic equation that we know it, so from the same example that we did it, so we're going to use the same equation here, same equation, but we have different. So I'm going to use the same equation. Now before that, what do we need here? We need to find the answer of this value, which will be a. So in the quadratic equation, this stands for a. This is the a value, this is the b value, and this is the c value in the quadratic equation. Well, let me just simplify the answers in order to see and to use the quadratic equation. Now here we will find 2as. Sometime the as, one of them will be negative, sometime both of them will be positive. So in the case of both of them positive, one of them will be too big. This is similar for a, when we were doing for a. So this became 17. A became 17 here. I can directly do it here. A 17, b value. Remember, this is not the a in which we know it compression block. No, this is just for this equation of quadratic equation. Remember, this is not the a that we were finding it in the compression block. So for the other part, which we have, 420, and then we have this value, and plus we have 325.44 e to the power 6. So this is value of c. Indeed, we have the first value, we have a minus for it, and the last value as well, we have minus. Now, as you can see from this minus, we have it, then minus the first one. And you can do this one with calculator, as I told you. If your calculator can do direct, so you can directly do it. If not, you can use this quadratic equation, as you can see it from here. So whether you use your calculator or program Excel to do things for you, it's still similar. So when this is 1 AS, the second AS, if I do it, because remember we'll have two, one of them will be plus, one of them will be minus here. So one of them is 1,768, the other one 10,343. Now which one you're gonna use? You'll use small here. 10,000 does not make any sense to be used, so 1768 is the one that we will use it. And if you remember from the previous one, we got the same answer as well. So 1768.71 after solving. AS will be 1768.71 millimeters square. If I'm not wrong, 178.68.71. You can make 72 even here, it won't be a problem. 72 millimeters square. Now this is with this approach. I found AS. Yes, I found AS. So what I have to do here, now in this approach, when you found AS, you will go and check AS with AS minimum and AS max. Now the same thing, it's true. You have to apply the knowledge that you have it. This is we call AS required. This is the required AS we have it. We call this one AS required because we need this one for the moment. So we know that AS required supposed to be greater equal to AS minimum and should be smaller equal to AS max. I'm not gonna repeat those two procedures because we already did it in so remember here, look, I'm reaching where? I'm reaching to the AS. Exactly similar values we have it, a few points difference. So you're still gonna check AS minimum, AS max. We already did AS minimum, AS max. They're not gonna change the same procedure. So we know that AS minimum is 388.7. So I'll directly bring it here. AS minimum 388.7. 0.7 millimeters square. So our AS indeed is greater than this one. You can just write it greater, which is our AS 1768.72, and it is smaller than AS max, which we found it there. Remember, with AS max, we said that's 0.75 AS balance, and AS balance we had an equation here. You see the AS balance here. So AS max 2271.09. Now 71.09. Now here again the same concepts valid. If AS required it's smaller than AS minimum, you will use AS minimum and you will continue. If AS is bigger than AS max, in that case you will say that double reinforcement should be used. And double reinforcement, you still don't know how to use it, so we'll keep it this way. If it comes, we will design double reinforcement later. We'll show it to you what will happen in case if this is bigger than this one. We will change something, or we will do the procedures in different manner to design the beam. So here I got the AS, it's totally fine. Now I can do the checking. Yes, I have AS, I can find A, same approach. So I'm gonna go and find AS. We have to check now, yes? So we have to check basically for what? Check to see if we started all of this by Fs is equal to Fy here. So I have to check basically. Or some books they said that use this AS and do analysis. Directly do analysis to see what will happen. Now if the analysis does not pass, then you will come back and you will change something from the design. I will not recommend that one because you need to understand if you do analysis. I mean, let's say you use this AS and you found some steel bars, you put it inside the section and you will do analysis. Now you have to know if the analysis does not pass. I mean, how do I know the analysis does not pass? You'll find the capacity, and if the capacity of the beam is smaller than this 325, it means that the beam in this section does not pass the design, because our capacity after designing shall be greater than 325.44. Now if it is not greater than this one, then we know that the design failed. But before going there, I prefer in this manner to check to see whether the design procedure we have at here assumptions are correct or not. So I will find some check. I'll do the check. The checking basically will be what? For Fs equal to Fy, for phi equal to 0.9. This will check those two basically to see whether what we have to do if they are not equal. We can come back and change from the beginning of the design. So now I will start with the checking. Since I have AS, I know that A is equal to what? AS Fy 0.85 F prime CB. We know this one, so I'm going to put AS that we found it here. But still we are assuming Fy, F is equal to Fy, yes? So we will find A, then we'll check to see whether it's true or not. So 1768.72 times 420 times 250 here. Now A should be similar to the one that we found it. So if I just use the value that we have it here, now let's just write it down as 1700. So 166.46. I can say 47. 166. millimeter. Then we shall go for C, because we need C to check to find strain. C is equal to A over beta 1, where beta 1 from table 4, look, I'm writing it here, 4 F prime C equal to 21 will be, so we know that from the table, if you go to the table, beta 1 will be 0.85 here. Well, we'll find C as 166.47 over 0.85, and this will give me 195.84. I'll continue checking the diagram. As we know, we see the diagram that we have it. We draw the strain diagram. No, we only assume one layer here, so only do is the top, do the bottom. So this will be ES. Now this is D minus C. So we're writing it down as the way we know. We have D, we have C. And I believe we did the same thing, if you remember, the same approach when we found A. Let's check to see A, the one that we found A here. We found A to be 166.46, so it's same thing, C 195.83, so you expect to have this 0.0057, the same thing. So kind of we come back to the same but in different approach. So we have will come out as 0.0057, and we can get absolute Y, which is Fy over ES, 420 over 200,000. That's going to be 0.0021, and since it's bigger and we have only one layer of steel, so you remember if you said one layer of steel you have it, we assume in the beginning one layer, this is equal to epsilon T. So since the two check that we have it here, since epsilon S, which is 0.0057, it's far greater than 0.0021, which is EY. Let's write it down as EY as well. Epsilon Y, which is 0.0021. So Fs is equal to Fy. Indeed. On the other hand, which is epsilon T, here since one layer it's the same value, it's greater than 0.005, the limit in the code, so phi also equal to 0.9. Now this is an easy example because everything seems to be the way that we assume them. So but in the homework that you have it, when you do, things are going to change. So I will expect from your understanding to see what will you decide for those things, or what will you do. And if you have any question, we'll say that. So what will happen if, let me say it again, in here, what will happen if Fs is not equal to Fy? So here, if is not equal to Fy, what will happen? Now, I can go back to the beginning of the starting. What we did here, where is the Fy? We have it here. We shall change this one to Fs. And if I change it to Fs, what will happen here? Now, if I change it to Fs, what will happen here? I don't know Fs in that case. And if I don't know Fs, I don't know Is, I have to find a way to change that Fs also somehow to A, bring it back to somewhere. That's why I told you need to know both approaches. Sometimes it will be helpful to try with different approaches if one of them didn't collide. If you remember in the first approach, in here we said that in this approach here, if look at here, Fy wasn't a part of the equation here, Fs Fy. It doesn't affect here. It will affect later. It will affect later. If you followed what we did here, it will affect later if it is not equal. So in this approach, however, it will affect the finding AA. So you have to come back and find something if they are not equal. If they're not equal, you will do something. You'll come back and maybe use the first approach A, and from there you'll find AS. What if the phi is not equal to? Now this phi here, we said that we'll find a new phi directly from here. We'll find the phi and we'll go back from the beginning. We'll change the 5.9 to that one and it will repeat the procedure. In that case, we will accept the second trial for phi. Let's say phi here will not be equal to 0.9. We'll find a new phi will be 0.8. We'll go back from the beginning. We'll go back this here. I'm on right here, so directly we'll come back here. Instead of this one, we'll write point. So here we put 0.9. We'll put 0.8, and you will find a new AS. You'll check the same procedure. You'll already have the minimum, maximum. You'll check it if it's between them. Then we'll find a new A, new C, new AS to make sure that the Fs will be equal to Fy. Then for the phi, it will be close to what you start with. This is the two things we have it. Now, again, we have AS. We can follow the same procedure. I'm not going to repeat it. So the AS is okay. Everything is correct. So this AS will be the one that we're using it for the design. What will happen? The same procedure. You will start finding that, which you already did. You know how to find the bars, checking the spacing. We decided to use 3 phi 27. And this is you can do the analysis. So doing analysis to see exactly how it will be the capacity, you will use 3527. D, we already showed to you, this is the new D, 571.5. You have B, you will find mu. I shall do this one here. So I'm taking this because we already designed it. So this will be the same design. I told you that I used a similar approach here and I didn't change a lot of things. So let's say after choosing the things, so let's say after choosing, this is what we have here. This is what we have here, and D is equal to 571.3, if I'm not wrong, 0.5. So I will start analyzing this one to see how much the moment will have it here. Well, first we need AS. Since we changed the numbers, I prefer to go in this way. 3 times pi over 4 times 27 square. We will have a small difference in the AS, if you remember, because we changed the number of bar. We have to use the integer number, so the AS is going to change. AS is going to change here. If we calculate this AS here, so let's calculate it somewhere here. We'll have 1717. Correct, yes. 3, 27, 27, yes. We have 1717.66. We'll have 1717.66 millimeters squared. This is the AS. We'll find A. A is equal to ASFY 0.85 F prime C B. So the only thing changed here is AS. So I'm going to change the AS here to 1717.66. Now A will be 161. 161.66, and this is millimeter, and C will be A over beta 1. Beta 1 is still 0.85, so 161.66 over 0.85. That's going to lead us to C, which is 190.19 millimeter. We shall continue checking still in analysis. You will do the same procedure. You will check to see if actually Fs is equal to Fy or not. In the design we already know that with this steel will be equal, but in the analysis, after changing the steel, even though if it's small changes, you have to check again to see whether they are correct or not. So this is epsilon S, which is epsilon T as well. Now D here somehow changed. It was 517 at the beginning, because after that became 71, and then this is D minus C. Well, procedure is still similar. 0.003 over C. Now D, we have 571.5 minus C, 190.19 over 190.90. So we'll see it here to see how much will come out. This time will be a bit different because of the C and the D, the difference between them. So it'll be 0.0065, 0.006. Epsilon S became 0.006. Still, it's bigger than the epsilon y, because epsilon y, which is 0.0021, we already calculated while design. So epsilon S is greater than epsilon y. So Fs still equal to Fy, no problem. And then we already know that this is equal to epsilon T, it's the last layer, and it is greater than 0.005. So Phi also equal to 0.9. Then, if everything goes, I will directly go to find what? To find Phi mu, which is equal to Phi mn. Now he will realize that if you made any mistake or not, to see if actually true or not. 0.9, we'll write AS. So if I write this one like this, Phi nt z Phi AS Fy zd minus a over 2, which will directly go for values. So we have 17.66 times 420 times d 571.5 minus 100a was 161.66 over 2, and we said this one will be Newton millimeter. I have it here, 10 to the power 6, in order to make it kilonewton dot meter. Now I shall write down these values to see what will be there the moment that we have it. Now this is after design. 17. Hopefully not have any problem. We have 318, so we have a small problem here. 318.58. I like it. So to see what will you do here. Now we did this analysis, yes. This is what we got with mu. We got this one with mu. 318.58. What was the mu that we started with? 325. Now what will I do here? Now the capacity of the beam that I have it is smaller than the applied moment, 325, which is not acceptable, yes. Now at this stage here, what will we do? We'll say this is smaller than mu applied, so it is not acceptable. It is not acceptable. Now, what will be the problem here? Let's discuss the problem, yes? Now, what did went wrong? Everything was correct, yes? Let me just highlight you what we did that makes this problem here. It's very small. I'm happy that we saw this one, because it's very small, but you realize that what does this small thing is going to change. Do you remember here when we calculate n number of bar, it was 3.08 and I rounded to 3, yes? Now it was too close to 3. I said 3, let's change it to 3. Now I was hoping that the d, which we assumed 570, here became 571. It might help me to overcome this small amount of steel bar here, but unfortunately it couldn't. Now if d came out, for example, 575, it would have helped me. This small change would not make any difference, but here it made difference. So what will I do here? We tried it 525 4 bars, it didn't fit, yes, with 4 bars it didn't fit inside here. Now in that case, what do we have to do? If I use 4527, it will not fit inside here. It will not fit inside this. So if I go for, let's say that 4 par 25 and I make it double layer, what will happen? Now double layer will change something as well. So in any way here you have to solve this problem. Solving the problem here, it will be where I cannot change B. Its architecture is asking B to be 250. And if there is another different bars I can use it, I'll try it. But we said that we use 22 will be 5 bars. It's 5 times 22 will be 100 something. And then in that case the spacing will still not be okay. 7 bar cannot. Here 9 bar still be problem, yes? Well, if I use this, shall I change this one to something else? I'd say if I told you that this is theoretically is acceptable, but practically I'm not talking about this one. Let's say if I go for 529 millimeter, what will happen? N will be 29 square. In that case I will have a different value. Maybe I will need, so let's say check with this one here, see how much this value will be. Now theoretically you have right to do this one here, so I can just simply change this value. Now here will be 2.6. If I use this one, I need to use 2.6, which we will round it up to 3. Now if I use 3529, most probably I will solve the problem. If I change this one to 3529, well, first thing first is checking the spacing to see if the spacing will be okay. Now if I use 3529, this will be 29 millimeter. The minimum spacing between them, 29 millimeter. So this will be not 27, 29. If it is 29, we'll come and check here what will happen. This will be 3 times 29. That's the only thing is going to change here. Then 3 times 29, it will be this 81 will be exactly. So we have it was 27, 2 will be 77 if I'm not wrong. 87 here, 87. So we will deduct 6 out of it, will be 63. Let's double check to be sure. So we have 3 times 29, that's going to be 87. So 250 minus 100 minus 87, and that's going to be, and then 63 divided by 2, that's going to be 31.5. So 31.5 in that case, this will be 31.5 millimeter. It is greater than the 29, which is 31.5 millimeter. So 3529 for spacing is okay. Well, now if I come back to the same analysis here, this time what will I do? Starting with not 327, I'll change this 329 here. What will happen? This AS is going to change. So I have 329 here. The AS is going to change. Will be 29, which will give me 1981 here. So 1900. Things are going to change. Everything is going to change. We'll check to see what will happen. Because I told you the design is not that much hard to change. So you realize that AS, if you try it, if there is a possibility, try to increase the AS. So here we increase the AS became 1981. But remember not to go beyond the maximum AS. 0.50, 56. Remember, this AS shall not pass beyond the AS max, which we know it here, 2271. It shall not pass this number. So remember, not too much increasing as well to be within the limit. Well, we're using this one to find ASFY. So we use this AS this time here, 1981.56. The rest will be similar. So I have 186.5, 186.5. And this became 219.41. So C changed, sure, is value here. For C gonna change. The new C will be 219, it's 219.41. We'll find epsilon S. Now, you might have problems always in the design. So the idea is how to solve those problems. Understanding is something. Now we have 0.0048. 0.0048. Well, we will have now a problem, yes? You will realize it. What will be the problem? It will be 0.0048. Yes, it's greater than if S is equal to Fy. But here, for this stage, this is smaller than. So smaller than 0.0. So this is not equal to 0.9. Look, I'm not gonna go and change the design. No, we'll find it's in transition, yes. Find phi, which is equal to 0.65 plus, if we have it from the slide, I should find it from the slide. This one in chapter 4. In chapter 3 we have the analysis. So we can use this equation to find the top will be 0.25 is the bottom 0.005 minus EY 0.0021 and then multiply by 0.00. We found 48, will be close to 9 minus 0.021. So here, if you find phi here, now here we don't need to go and change the design. Remember, we still want to see if the moment that we will find it, the capacity, if the capacity is smaller, then I have to go and change something else. But if the capacity of the beam come out to be bigger than what we have, then in that case we'll say no need for changes. So we have 0.883. I have 0.883. 883 here. Well, we'll do the same thing here, but this 0.9 will be 0.883. And sure, the AS already changed. We'll have a new moment to see what will be the moment that we have it now. We'll have 0.883. Look, you increase the AS, the factor of safety decreased. 1981.56. Sure, A also changed here. A became 186.5. Also, so maybe D also is changing a bit, but I didn't go for D as well, because 29 we have it. Maybe 29 kind of will not change that much. D here will be 0.570. That will be a small changes here, maybe 0.5 will be decreased here. But the main changes we have it here, those three, to see what will happen in that case if we have so changes happen to be in the phi, in the AS. So the idea here, increasing the AS will decrease the phi for us, and sure will increase the value of A. So it's not something to say always I can manage this one easy, but you have to be careful. We have it here, 351.45. 351.45 kilonewton. Now this time I can say it's greater than the applied moment, which is 325.44 kilonewton per meter. So I'm not saying not acceptable, I'll say the design is okay. Now, in this example here, we learned that even if the design didn't come out, there is no need to start from the scratch. There is some part that if I understand what I did, I know where to change it. So remember, all of this started from where? From at this point when I decided to change this 3.08 to 3. And I was hoping that to be bigger, but it didn't come out bigger. By the way, if you someone will say that this D will not be correct, sure, this D you can change this D. Why? Because if became 29, we can find a new D here. This will be a new D. We can find it here because it was 27 and you have 2 millimeter and 1 millimeter will be up, so this will be 70. It will be 570.5. I mean, that will not change too much because it will affect some of the small things here. I mean, this 0, this one will not, if this is 70.5, it will not affect too much here. For example, even here, this point, so small, the change we have it here. Even here, still will be, this will still be, maybe this will be 44 or 45. One will come out, still will be bigger than the moment applied. So I need you to understand here, when you increased AS, when we increase AS, what will happen? Look, phi decreased. The decrease in the phi, also this part here, A will increase. Now increasing the A, what will happen? This part will be smaller. But the increase in AS basically was more effective in the two decreases that we have it here. In this manner, the moment became bigger than the moment applied here, 351. So here, no need to go back to see, okay, I need to change something. No, the design is okay here. So we started with what? We started in the beginning by some assumptions. Those assumptions will lead us to something. But changing AS is very important. Please remember, when you have AS and you're changing it to numbers, number of bar, this is a critical thing that you have it. Try to increase, but not too much. And the idea increasing it depends on what? The spacing. You cannot just say, okay, let me choose this one. It had to fit in one layer. I recommend you try to see if it become two layer. If it became two layer, the H will change a lot. Sorry, the D will change a lot. Like this is for one layer of tension, yes. If it became two layer, you'll say minus 25 as well. If it's two layer, because between the two layer spacing will be a load minus something else as well. So if it became two layer, D will decrease a lot, and that will affect the solution as well. Someone can try, for example, one of these numbers here. Let's say choose 8 bar 19. Choose this one, but make it 8 bar. 8 bars. And if you choose 8 bar, what will you do? You will do it in two layer. Try what will happen. I mean, I need you, when you're practicing, not just over the thing and doing it, whatever comes to your mind. If I try, for example, 4 at the bottoms and 4 here. First, I will check to see, can I put 419 in the bottom? If I cannot put 4, then in that case, I will choose something else. I'll choose maybe 2 layer, something else. Let's say 22, I'll make this one 6 bars. Will be a lot, I'm changing it, but 6 bar, I'll take it 2 layers, 3 by 3. And then I'll do analysis, but the analysis will be had. Make sure if you change for 2 layer, D will change a lot. This D, you have to bring it to the center of them. So you have to take the cover, the stirrup, and geometrically you can find it by yourself, yes. You'll take the stirrup, you'll take the diameter of the bar, and here, assuming between them it's minimum 25 millimeter we need it. Minimum, this is the minimum we need 25 or 5 bar. Here, let's say if I use 22 bars, then this between them 25. I can take the half of 25 and I can get to find D. So I'll take this part out of it, which is the cover, the stirrup, 5 bar and half of 25. I can get to D. D will decrease a lot if you change to 2 layer. To see what will happen. Maybe in that time you increase the steel bar, but D changes. If D change, you will have ES and ET changes. Look, there will be two different strain and you will have different approaches. That's why I always tell the student, your design, it's unique to you. Whatever you do, you may end up with different solution. Try to understand if you change something, what will be the next step, what will change. Like here, if I decide 2 layer, D is going to change, and if I have 2 layer, I know that in 2 layer, ET not will be equal to ES. I'll have ES in the center, ET for the last layer. In the analysis, you will end up here, you will have ET and ES different. Will still be the same, but small changes will happen there. Well, I hope that those information will be enough to guide you through design. You have a homework, which I will extend the due date after 8, which is 23 basically. So you have around 15 to 23. You have around 8 days to practice these videos, both of them, and try the example that you have. Now, if any of you have problem with the design procedure, you can ask in the group. If there is something I can help, I will give you a hint. I'll try, okay, use this idea, but I'm not going to let you just give you the solution. I want you to try to see what will happen. Now, I don't want you to change the dimension of the beam unless it is necessary. Unless if there is no any option, then I can allow you to change, but not with any, like just suddenly. The sections not change. Why? Because we say the architectures applying this rule to us, the section to be the way that they want it. Unless it is necessary, then we'll change the section. And I hope one of you in the design will face these things. Now, each of you will have different approaches, different things. You may end up different design. but all we use the same approaches. So whether you use the first approach finding A or the second approach finding AS, but you'll realize that both of them will lead us the same solution. It doesn't matter which one we use. Thanks for listening.